Yeah, so I'm going to be talking about a new proof system with inspiration from SAT solving and with an unfortunately violent name. We couldn't think of anything better. Okay, so SAT is your canonical NP-hard problem, and this means that it's probably intractable in the worst case. Because of this, you might think that general-purpose SAT solvers, or really anything besides like an algorithm tailored to the particular instances of SAT you're trying to solve, should be out of the question. So contrary to this, the SAT solving community has had some amazing progress in the past couple of decades. So they're able to solve multitudes of real-world instances consisting of up to millions of variables and often running in near linear time. And they're currently used in practice in model checking, planning, and bioinformatics. So most of the state-of-the-art SAT solvers are based on the conflict-driven clause learning algorithm, which is a modification of the basic DPLL algorithm from the 60s, augmented with a bunch of fancy heuristics, as well as a couple other tricks. So DPLL is the most basic backtrack search algorithm you can think of. You start with a CNF formula, and you want to find a satisfying assignment. So you pick a variable. You branch on whether that variable is true or false. And so setting x1 to false doesn't falsify or satisfy the formula, so we recurse and we do it again. Now setting both x1 and x2 to false. This does falsify the formula, and so we should halt this recursive branch. And we're also going to label the leaf with a witness of this fact, so just a falsified clause. There. And so continuing recursively, we can derive the full DPLL tree like that. And now observe that every leaf is labeled with a falsified clause, and this means that there was no satisfying assignment to the original formula. So we can take the DPLL tree as a proof of this fact. And as was mentioned in the previous talk, this is a common theme amongst these SAT algorithms. If they halt without finding a satisfying assignment, then you can take their execution trace as a proof of the fact that the formula is unsatisfiable. And for certain SAT algorithms employing certain types of reasoning, the proofs produced by these SAT algorithms can be captured by formal proof systems. And so analysis from proof complexity can be carried over to these SAT solvers. And in this case, the length of proofs in these proof systems capture the runtime of an ideal implementation of the search algorithm. Okay, so DPLL is one of these proof systems or search algorithms. So it's equivalent, the proofs it produces are equivalent to the proofs produced by tree-like resolution. The main difference between them is that DPLL is query-based, so you branch on the truth value to a variable, and resolution is rule-based, so you iteratively apply a set of inference rules. Although this difference is subtle, we believe that it's quite important. It's intuitively much easier to make heuristics for query-based algorithms than these complicated rule sets. Okay, so CDCL is in a similar position. Although it augments DPLL with a bunch of fancy heuristics and clause learning, random restarts, and more, the proofs it produces are still captured by the weak resolution proof system. So resolution's one of the weakest proof systems we study. For example, it can't even count, so we have exponential lower bounds on the size of proofs of a bunch of different counting principles. So counting is a pretty basic form of reasoning that we have, and you'd think that this would severely limit DPLL-based algorithms. Because of this, researchers have started looking at SAT solvers based on stronger types of reasoning. The most common of these is pseudo-Boolean solvers, which reason about integer linear inequalities. And they're based on the cutting planes proof system, which is quite a bit stronger than resolution. But even so, they haven't been able to get performance nearly close to the performance that is seen by these DPLL-based solvers. Okay, so this is kind of a weird situation. We have a bunch of strong proof systems, and we also have theoretical results which say that we can find proofs in these proof systems in deterministically and efficiently. But still the best SAT solvers that we have are based on DPLL, which is equivalent to the weakest proof system we study. So why is this? Well, our hypothesis was that querying is just so much more conducive to developing like good heuristics than these rule-based systems, that they can overcome the weaknesses posed by being equivalent to tree-like resolution. So for example, querying leads to really simple divide and conquer style algorithms, which is one of the nicest algorithm paradigms we have. And it's kind of like the difference between DPLL and tree-like resolution. So even though they're equivalent, all of the upper bounds and algorithms based on tree-like resolution are all developed in DPLL because it's so much easier to reason about. Okay, so because of this, we introduce a natural generalization of DPLL to reason about integer linear inequalities, which we formalize as a proof system called stabbing planes. So what is stabbing planes? So we begin with an unsatisfiable system of linear inequalities. And by unsatisfiable, I mean over Boolean assignments. We also have constraints that say that the variables take value within the 0-1 interval. And so because we're dealing with linear inequalities, we can associate a polytope of fractional solutions to the original system of inequalities. So I've plotted this here in green. And the black square represents the two-dimensional Boolean cube. And observe that the polytope doesn't touch any of the vertices, so it doesn't have any Boolean solutions to it. Okay, so similar to how DPLL is allowed to branch on an arbitrary variable, stabbing planes, you're allowed to pick an arbitrary integer linear inequality and branch on its truth value. So here I have the inequality x plus y is greater than or equal to 2. And so branching on this, you recurse on the left leaf by adding x plus y is less than or equal to 1 to the set of the constraints, and on the right, x plus y is greater than or equal to 2. And so geometrically, this corresponds to cutting out this slab here of points from the polytope. On the left branch, you recurse on the bottom half, and the right branch, you recurse on the top. And so this slab is removed, and is this okay? Well, yes. It turns out that any Boolean solution will satisfy an integer linear inequality or its integer negation. And so if the original system had any Boolean solutions, then they would have survived on one of these two branches. Okay, so going down to the left branch here, you see that about half of the polytope remains. So we're going to branch on another inequality. This time, x minus y is greater than or equal to 1. And this removes the last bit of the polytope. And so if you look at both of the two children of this node, they correspond to the empty polytope. Also, the one at the top right also does. And so we can use the fact that we've derived the empty polytope at all of the leaves here as like a certificate that the inequalities, like the original axioms that we had, and the inequalities along the branch to each of these nodes form the empty polytope. But we need some like easy to verify way to write this down. So a variant of Farca's lemma says that a polytope is empty if and only if there's a non-negative linear combination of its constraints, which equals 0 greater than or equal to 1. So we can use this as a witness. So we label each of the leaves with the non-negative linear combination of the inequalities along the path leading to that node, and also the original constraints, which equals 0 greater than or equal to 1. And because any Boolean solution would have survived down one of these paths, we can't we can't label each of the leaves with a witness if the original system wasn't unsatisfiable. Okay, so this also gives two different views of a stabbing planes proof. We have this algebraic view where we're recursively branching and we want to derive 0 greater than or equal to 1 at each of the leaves. And we have this geometric view, which is kind of like a recursive cover of the original polytope. So we think that's quite nice. The two complexity measures we're going to be looking at are the size, which is the number of nodes in the proof, and the depth, which is the tree depth. Okay, and so I mentioned that stabbing planes is like a generalization of DPLL, but let's formally see this. So using standard techniques, you can represent a CNF using a set of linear inequalities, like that. So it's equivalent to the set of, or to the original CNF, and we also replaced each of the equality queries along the leaves. Along the branches with the with inequality queries or stabbing planes queries, and together with the constraints that each variable falls in the 0-1 interval, this is equivalent to the original one. And we also just need to change the witnesses set the leaves to stabbing planes witnesses. And you can see if you add up each of the witnesses here, they equal 0 greater than or equal to 1. Okay, so stabbing planes is a formal generalization of DPLL. And similar to how DPLL and tree-like resolution are query and rule-based versions of each other, we show that stabbing planes does have an equivalent rule-based version. So it's equivalent to a tree-like variant of the RCP proof system introduced by Krychek. But even so, we think that this query viewpoint of stabbing planes is still quite valuable. In particular, we're able to show some really interesting upper bounds. So the most interesting of these is that stabbing planes has quasi-polynomial size proofs of any system of linear inequalities over a finite field. So I'm going to show that to you because it really illustrates how nice stabbing planes proofs are. So we're going to do mod 2 because it's the easiest, but it generalizes in a straightforward way. So suppose we have some unsatisfiable system of mod 2 equations. And since they're unsatisfiable, there exists some subset of them which sum to be 0 equal 1 mod 2. So we're going to restrict to those. And now the idea is that if we split the set of constraints into two sets, then under any Boolean assignment to the variables, at least one of the two is going to contain a falsified constraint. And furthermore, the sum of the constraints in each set, the value that this takes on, tells us which one. And to see this, first observe that both of the sets sum to the same value, x3 plus x7, and they have to be equal, at least at the first step, because the whole system is equal to 0 equal 1 mod 2. Okay, and now the first, the green set requires that the parity be even, and the pink set requires that the parity must be odd. And so if we can determine the parity of that equation, then we can recurse on the one where it's falsified and eventually search for a falsified constraint. Okay, so that's going to be our algorithm. So we're going to split the set into two equal sized sets. And then we're going to determine the value of the constraints in each set. And to do this, in stabbing planes, we can just query, is the sum of the constraints greater than or equal to 1, greater than or equal to 2, all the way up to the max value it can take on. This is going to be at most a linear number of queries. Okay, and then finally, we just recurse on the set which contains a falsified constraint. Okay, so for an example, suppose that we learned that x3 plus x7 is even, and so we recurse on the pink set because it wants odd parity. And now we half to the constraints. And so the sum of the constraints in the first one is this big thing, x1 plus x2 plus x3 plus x4 plus x5 plus x7. And in the pink one, it's x1 plus x2 plus x4 plus x5. And suppose that we learned that we determined that it was even again, and then we recurse on the pink set again. And then finally, we have a single constraint, and we've derived that its parity is even, but we have a constraint saying that its parity is odd, and we can use this to derive 0 greater than or equal to 1. So some analysis. Each recursive step takes at most a linear number of branching, and and there are at most a logarithmic number of recursive steps because we're halving the constraints each time. Okay, so besides being motivated from the perspective of SAT solving, we also think that stabbing planes falls nicely into the proof complexity literature because it has quasi-polynomial sized proofs of any system of linear equalities over a finite field. It has quasi-polynomial sized proofs of the Seiton formulas, which are a hard family of formulas used to prove lower bounds on many strong proof systems. They're also required, or conjectured to require exponential sized proofs for cutting planes. Furthermore, we showed that stabbing planes can simulate cutting planes, meaning that we can turn any cutting plane's proof into a stabbing plane's proof that's not much bigger. This is sort of surprising because stabbing planes is a tree-like proof system, whereas cutting planes is DAG-like. And finally, we showed that a near optimal depth lower bound on the depth of stabbing planes proofs. This is via reduction to real communication complexity. And we show that this is unlikely to work to give stabbing planes size lower bounds. And two reasons why. We show that stabbing planes proofs can't be balanced. This means that you can't take a stabbing planes proof of size s and turn it into one of depth log s. Also, we show that real communication protocols can't be balanced as well. So this kind of positions stabbing planes at the barrier of where we can prove lower bounds. While we show we can prove depth lower bounds, and it simulates the proof system cutting planes, which is the strongest semi-algebraic proof system for which we have lower bounds, it doesn't look like current techniques are going to be able to be used to prove size lower bounds. Okay, so open problems, super polynomial lower bounds on stabbing planes proofs. So we show that stabbing planes size, or we measure stabbing planes size as the number of nodes, but we're not actually sure whether this is equal to the bit size needed to represent the proof. To show this, we would need to show that each inequality in the stabbing planes proof can have its coefficients represented with a polynomial number of bits. So this is the case for other integer linear inequality-based proof systems, such as cutting planes. And furthermore, there's a result by Moroga from '72, which says that any integer linear inequality separating two subsets of Boolean vectors can be represented by a polynomial number of bits. So we're hoping that this can be modified in some way to work for stabbing planes. Next is separating cutting planes and stabbing planes. So the candidate there is the Seiton formulas because they're conjectured to require exponential size proofs in cutting planes. And finally, we think that stabbing planes is a good proof system for developing good search algorithms on because it generalizes DPLL. Hopefully that you could, as a first step, maybe generalize the really good heuristics for DPLL to work for stabbing planes-based solvers. Okay. Yep.
Do you think quasi-polynomial is the right answer for solving linear equations?
In stabbing planes, I can't see a better way of doing it. Since they're so general in stabbing planes, really has to do this sort of divide and conquer. I think the only place you'd be able to improve would be in determining in doing each recursive step, and I don't see a better way than just querying is the value of the constraints equal 1, equal 2, so on.
Why stabbing planes?
Why the name? Okay, so cutting planes, that's where we started. And then you have this, so if you go back, you have this polytope here. And each recursive step, you're kind of like stabbing the polytope with a slab that you're taking out. Yeah. Paul Beam suggested this name, and then we spent about half of our time trying to figure out, like, can we get a better name than this? Are we really stuck with stabbing planes? So yes, we are stuck with stabbing planes.